actually may be the largest of your homework problems, that's for sure. There are a lot of interesting things going on here. There is friction, which is dry friction, which is part of what we're going over in this section. But in addition, there's some basic statics as well. Will that sawhorse tip over? And take a look at basically the legs are 2 feet apart, and what kind of moment resistance does that provide by having that brace, instead of it being just something like a column that's standing straight up. Instead, you have a little bit of distance between the legs, and that turns out to be very important to resist overturning, right? That's the whole value of having one of those little sawhorses. So here we are. We decided to put a board or a ladder, putting that down on top of the sawhorse, and then on this end, we're holding onto it and we're pushing. So it doesn't matter how hard we push, but what we're trying to find out is what happens first. Will the sawhorse slip on the ground, will it go, or will the sawhorse tip over, or will it stay put and just the board slide over the top of the sawhorse?
I don't think
3
that ever happens.
possibilities. What's that?
I've never seen that happen.
It's never gonna happen. It's gonna flop over on you.
Every time I try to slide wood on a sawhorse, the sawhorse tips over.
The sawhorse has got to tip over. That's the rule.
What's that?
By observation.
Exactly, yeah.
I know.
My previous experience.
Every time.
By observation.
You could have bearings on that and it'd still tip over.
So we have a board that is 18 feet long. And at this instant, the sawhorse is positioned so it is 14 foot of a span between point A and point C where the sawhorse is at. I don't know that actually is a big issue, the 3 foot, because that is the moment arm for whatever force this is here, the push force. That's going to be the moment arm for the overturning. We have 3 pounds per linear foot. This is a heavy board. It's a thick oak. So then we have a coefficient of friction on for the sawhorse and the ground, or the floor in your shop. We have the sawhorse itself is a pretty heavy sawhorse, 15 pounds itself, right at the center, at least vertically speaking. And then we have friction between the board and the top of the sawhorse that's 50% friction. So what's going to happen first?
It's going to tip.
It's gonna
That
tip
friction's
first.
greater and it's heavier.
Tip or slide. I'm looking at this, the coefficient of friction between the bottom and maybe your concrete floor is actually pretty low, 30%. This coefficient here, 50%. Yeah, that's pretty good. So, well, we're going to have to go through this and study it piece by piece and work our way through it. So what did I do first? I decided to do a free body diagram of the board. So let's start with the board. The board is 18 feet long, and 18 times 3 is 50 pounds. So what we could do is discover what our reactions are first thing, because that gives me an idea of what's going on. If I know what my reaction here is at C, basically, if I know how much the sawhorse has to hold up, well then, half of that would be the friction force that's available, right? We have a 50% friction between the board and the sawhorse there. So whatever my normal is, or whatever at C, whatever we're holding up at C, half of that is what we have in friction, available friction, which is a really good starting point. So let's just run through our traditional statics, just like this was a beam that was being point loaded right here at halfway, so that's 9 feet over, right? 9 feet over, we have a point load that's 54 pounds. And then we can run our calcs, then we can get back to things. So let's see here, I started writing my equations. I said, well, I'm going to take the moment about A so I can discover what my force is at C, my supporting force at C. So if I take the moment about A, first of all, that friction force goes through it, that A force goes through it, that A force goes through A. So we have only two forces that can cause moment. We have the 54 pounds going this direction, which is the opposite of right-hand rule, so that would be a negative rotation. 54 pounds times 9 feet over. Then we have some unknown force out here that's actually supporting it. It's causing a positive rotation, at least for right-hand rule. It's trying to move it around A in that way. So, but it's 14 feet over, and it's some unknown force. I brought this over to the other side. That would actually be a negative on both sides, but I dropped the negative signs on both sides. Divide both sides by 14 feet, and I'm left with 34.71 pounds. So the normal force, the support that at this instant, the sawhorse must hold up 34.7 pounds. And we know that the friction is half of that. The potential friction between the board and the sawhorse would be half of whatever the normal force is. So that friction at C, the maximum could be is half. I went ahead and just wrote that. So the friction at C would be half of 34.71. So I've got 17 pounds. Now, if I get anything beyond 17.36 pounds, the board is going to start chattering and slipping, right? If the sawhorse stays still, the maximum friction that could possibly happen at this instant is 17.36 pounds. So that's the maximum sideways load we're going to have on that sawhorse at that instant in time. And anything over that, and it's going to start sliding. And then, as we know, the coefficient of friction for something that is moving actually drops down. This is a coefficient, they didn't specify that it was static, but that's the situation with static friction. All right, do I even need to bother with the forces at A? Do I even need to? The whole analysis is here, maybe, if you think about it, I have to look at, I don't know, we might have to, but they wouldn't be too difficult, right? Summation of forces vertically, I could figure out AY, and then the summation of forces horizontally, well, whatever that friction is, this would be the opposite. So you can figure it out pretty quick. You think about it, if you're pushing right here, AX, and if it starts to slip on the top of that sawhorse, well, the maximum you got to was a sideways push of 17.36 pounds before it started to slip. But we don't know that. It might flop over before we even get to 17 pounds, which you guys are all voting on right now. Pretty much everyone's voting for the tipping rather than slipping at the top. And I don't know. We'll see. Can't give you a hint. All right. So at this point, I have studied, because you do this, you work your way in piece by piece. Start for something that you know or can figure out, and you work your way in piece by piece. So at this point, I know the maximum force that can be delivered by friction here at the top of that sawhorse would be that 17.36 pounds. That's it. Anything more, it's either less than that when it tips, or anything above that, the board starts to slip on the top of the sawhorse. So that's it. That's the highest we can have sideways force. So the next thing I did is I went in and I just thought about the sawhorse itself. I just wanted to do a free body diagram of the sawhorse and see what I could discover. So, for example, if I put the maximum sideways force on it of 17.36 pounds and it doesn't tip over, if somehow it can actually resist that, well then I know slipping on the top is not how it's going to fail. So that's what I'm doing now, is I'm kind of working my way in. All right, let's see what we've got here. So I realized that my downward force is, at this point in time, it's 34.7 pounds, right? That's what we discovered right here. Because we're pushing up. If we look at the board itself, it's being pushed up on this end or held up on this end. But if we look at the sawhorse, it feels like it's being pushed down by the same amount, 34.71. It's just your reference, right? Your point of view. So then, the maximum sideways force that we could have is that from that caused by that maximum friction was 17.36 pounds. We also know that our sawhorse itself weighs 15 pounds, and that's right at its center. So then the question is, what would be the maximum force that the floor can provide? Ooh, interesting. So if I know this weight, 34.71, And I know this weight, I can add that as well, that's 15 pounds, 15 plus, so it's roughly 50 pounds, right? If the floor provides a 30% friction, what's 30% of 50 pounds? Yeah, is that, you know, gonna be something different? Yeah, exactly. So what is the maximum friction that the floor can provide, right? We've got a 30% friction that the floor can provide. And the thing is, though, we have more weight. We have 15 pounds of additional weight. The sawhorse itself plus the weight of the board is on it at this point. But we have a less friction. We have only 30%. You changing your mind now? You think
I'm
it's going to
thinking
slip on
about
the
it.
floor?
I'm thinking,
The floor might slip? All right, well, let's find out what that is. And what would be the normal here? Well, that would be equal to all the weight going down. We got to hold it up, right? So the ground has to hold up what all the weight coming down would be. So let's write the equilibrium equation. In the vertical, I've got 34 coming down plus another 15 coming down. There you go, minus 15, minus 34. So bring the n over to the other side, drop the negative signs. I got 49.71 pounds coming down, so the normal has to be 49.71 pounds pushing back up, of course. This friction right here, the maximum friction that can be delivered is 30%, right? 0.3, that's your friction coefficient, 30% of whatever the normal is. Whatever the floor is holding up. What is 30%? Let's see here. Oh man. So we're a little closer though, but we could still have overturn, we could still flip over. So at this point, we now know that the sawhorse will actually slip on the ground first before on the top it slips. Because we will never get to that 17.36 pounds, we'll never get there because the bottom starts to slip at 14.91 pounds. So since the maximum floor friction is 14.91 pounds, which is less than the maximum friction between the sawhorse and the board, we now know that the sawhorse legs will slip before the board slips on the top. So we can throw that one out. Now we have to do the tipping check. Because now we know that the maximum we'll ever get to would be 14.91 pounds on the top and 14.91 pounds on the bottom, right? Do you see how that's like a force couple? Do you see how I've got a force on the top pushing this way, and I've got a force on the bottom pushing it? This is why your sawhorses flop over all the time, guys. Because the bottom, when you're pushing on it sideways, the floor is trying to hold it back, so it's causing a force this way, and your push on the top is this. You are actually, it's like doubling the overturning, right? You've got a force on the top and the bottom going opposite. You're causing a moment, a force couple. So, complete disadvantage. But, let's think about this, because there's got to be we have a sawhorse that's 2 foot wide, if I remember. Yep, we've got a 2 foot wide from leg to leg, and we would we'd have to calculate an overturning moment, so let's check this out. All right, so I'm going to sketch it. I have a force of 49.71, and if you think about it, right before the sawhorse flips over, the leg on this side is supporting everything, right? At the instant, there's a point where if you're watching that sawhorse right before it flops over, you're going to notice that there's that moment where it's right when it's starting to tip, the leg on this side actually comes off the ground. Right as it's starting to go, right? The leg on this side comes off the ground, so that means all of the load is on that one side at that instant. So that's what we're talking about. When you're pushing and you've got 14.91 pounds, it's about ready to slip on the floor, and it may overturn. That's what we're trying to check right now. Does it overturn at that instant when all the force is on that side? Okay, let's see how that works. So I have 34.71 pounds coming right down through the middle. I've got 15 pounds coming right down through the middle. And I've got 49.71 pounds going up this way here. Okay. And then I have these forces as well to contend with. Let's see how I approach that. All right. I decided to take the moment about 0. Interesting. Okay. If I do that, then I have a bunch of forces to deal with. The first thing I can tell though is the friction on the ground, that 14 pounds of friction that's on the ground goes right through this 0 point. I think in the actual book they called that out as 0, didn't they? Yeah, for some reason they called this little corner on the sawhorse 0. That's cool. All right. So if I take the moment about that 0.0 right there, this friction force that's the floor goes right through it, so we can ignore that one thing. But we have a whole bunch of other stuff we got to deal with. So we have 34.71 plus another 15 pounds all coming down right through the middle, which is 1 foot over. It'll have a 1 foot moment arm. So there's 49.71 pounds going down with a 1 foot moment arm. That would cause, or try to cause, a negative rotation. So if I'm looking at right-hand rule being positive, this is trying to go the opposite of that. So that's why I put a negative sign in front of it. So I have 49.7 pounds going down, and I'm 1 foot over. Then I have, do you see that friction force at the top? That's the force, the board, holding onto the top of your sawhorse, and you're pushing on that. You bet you've got, and if you remember, it was a 3 foot height, the sawhorse was 3 feet tall. So we have 14.91 pounds that has a 3 foot moment arm and is trying to cause you to rotate this negative way. So that's why I put a negative sign on it. So minus the force at C, which, oh, interesting. Do you see how I did not define it? Because I'm not too sure. It might actually overturn before we even get to 14.91. So the top slides when we were at, what, I can't remember, 17 pounds. The bottom starts to slide at 14.91, but there's a possibility we might overturn before we even get to 14.91. In other words, the floor, it holds on the floor and it just flops over. That's a possibility. So, because I don't know the answer, I'm going to, instead of calling this out as 14.91, I'm going to call it out as something unknown, an unknown force in the sea. It's 3 feet away. Then I've got 40, I do know something. If it's about ready to overturn, then all of the load that was here, there would be nothing that's on the floor here. It's about ready to lift off the ground, so there would be nothing here. All of the force would be on the other leg of your sawhorse. So that's why I'm putting 47.71 pounds, 2 feet over. The nice thing about it is 2 feet over, but it is trying to cause it to rotate the opposite way. It's the only thing that's holding us back. It's that one leg on the other side. Of course, it's just like you when you're standing on your feet and you roll forward and you're on your tippy toes. The only thing that's holding you from flopping over is your tippy toes, right? Same thing here. The only thing that's causing this from flopping over, because the heel is up, it's the tippy toe on that side. So at that point, all the force is being held up on that one side. It's 2 feet over, so I have 49.71 pounds going up, and it's 2 feet over. So I brought this over to the other side, which made it positive, and then subtracted this from that, leaving 49.71, divide both sides by 3, and at 16.57 pounds, which is actually greater, 50 or greater. So here's the 3 conditions. The first condition is it takes 17.36 pounds for it to start to, for the board to start sliding on the top of the sawhorse, and it never gets there. Then the other thing that we discovered is for the sawhorse to start slipping on the ground, all it takes is 14.91 pounds. And now we just discovered that in order for it to tip, it takes 16.57 pounds. You have to push 16.57 pounds. We never get to 16.57 pounds. We actually start sliding on the floor once we get to 14.91 pounds. So the answer is slide. However, tip is close. So if there's something on the floor that it gets stuck on, just anything at all where it increases the friction. If the friction just increases a little bit, you're going to flop over. So if you got that polished concrete floor with a 30% friction, it's just going to start sliding across the floor. But a little bit of extra friction flops over, and it would take a lot more than that to get it to start sliding on the top of it. So There's the answer. The answer is, it will slide, the whole thing, the board and the sawhorse will slide first on the ground. Chirp across your polished concrete floor first. So there we go. When the push is greater than 14.91, we'll see sawhorse leg start to slip. Have to get up to this or this before something else will happen. Since the carpenter is slowly pushing it, sawhorse legs would be slipping and the entire unit would all move together. This is a great way of transporting something around your shop, right? Put it on the sawhorse and slowly push it across the shop floor. That's what we're talking about here. But you're playing with fire. You're pretty close to overturning. Just need another 1.5 pound push and you're gonna flop over. So that is, I think, of the 5 pages on the homework, that was 3 of them. That's the biggest problem for the last homework. Was that helpful to go over?
Yeah.
Oh, yes. Definitely. All right, I'm gonna record that one.